the previous module and it looked like what Josh shared in his slides, then by all means continue with your code. Otherwise, the files are available at the link that I've dropped into the chat, shown here. For this exercise, or for the exercises in this module, we're going to begin with module 2.2, version 2, in the last version that was built with Josh, which is the version loop. So I'm going to go ahead and open my version of that. I'm going to be working locally. Of course, all of this is available and usable in NanoHub. I'm going to open my simulation files first in Player, and then I'm going to launch Twedit and do the same. So module 2.2. I'm going to split my screen here real quick. Open simulation files to the module code, version 2.2, version 2, the loop version, and then Glacier model CC3D. And then in Twedit, I'll load that as well. CC3D project, open CC3D project, module versions, module 2.2, version 2, the loop version, Glacier model CC3D. Double click, everything opens. We go ahead and close the file glacier model.py. We're not going to be working with that. We will be working in both the XML and the steppable scripts. You can go ahead and leave both of those open. So if everyone's there, we'll proceed. And while everyone's getting things loaded, let's recap very quickly. So we have our epithelial sheet. This is the ODE model as we've spatialized so far. We've got an epithelial sheet experiencing the viral life cycle. So uninfected cells, infected cells, virus-releasing cells, and dead cells. We go through the process of internalization, viral replication, viral release, and virally induced apoptosis. And then we have our, from the last module, the extracellular virus and cytokine fields. And so they're spatialized versions of these ODE expressions, and then now discrete spatialized versions of the epithelial sheet. Of course, the cytokine signaling that is performed by infected and virus-releasing cells, that cytokine signaling that's happening in the extracellular space. Now we're going to map that to figure out how to get immune cells into our domain to go about killing some virus-releasing cells to fight infection. Now, I took a screenshot during the lunch break, and this is what our current module that we're working from, this is what this module looks like currently at about day 6.5. And in particular, you'll notice that we don't have immune cells at all in our population data plot. You'll notice in the total diffusive species plot, there's nothing for the lymph node. For the spatial results, there's the green line from the ODEs. We're going to generate the spatial version of that. And maybe most notably, in the population data, you'll see with the yellow line that after a while, due to the lack of contact killing, the spatial model diverges from the ODE model. And that's most apparent in population, or the death data window on the right. I've got a green line for contact ODE. That's an expression for the number of cells killed by contact cytotoxicity. According to the ODEs, we're going to implement that as well in a later module. Today we're going to set up by getting the immune cells in the first place. So as a very quick background, and I don't want to spend very much time on this, but in general, T-cell recruitment is quite complicated, as we went through quite a bit more in day 1 with immune cell or immune system signaling and recruitment. The basics that we're particularly interested in for this model is that cells at a site of infection, particularly infected cells, virus-releasing cells, and immune cells that we don't represent, they will signal, in our case, cytokine field. They undergo signaling to induce an organismal level immune response. Now, somewhere far away from the site of infection, specifically in the lymph nodes and the thymus. T cells will proliferate, they'll specialize according to the particular pathogen of an infection, and then they will migrate back to a site of infection. Now, those programmed T cells, when they arrive at the site of infection, they've been programmed to recognize antigen-presenting cells that have been infected, in which case they will latch to those cells and through surface interactions will induce apoptosis. So that's what we'd like to represent with the model that we're spatializing in this workshop. So the very basics of the modeling is that then we have infected cells that release cytokines. We'd like to see that those cytokines released by individual infected and virus-releasing cells induce a cascade of immune cell proliferation and then recruitment back to our local site. And then once those cells get to our site of infection, then the local immune cells will move around on top of our epithelial sheet, similarly to the big model that we discussed in day one. They'll move around on top of there and they will find infected cells, and then through contact interactions, they'll kill them. So to do that, in this specific module, pardon my phone, for this specific module, we're going to go through introducing a volume constraint, as well as contact modeling aspects. Probably most interestingly, in the spatial domain, we'll have cells that actually move around, those being our immune cells. And we're going to implement a sort of multi-scale scheme to do compartmental modeling of something like a lymph node, which is where cytokine signaling communicates information to T cell proliferation occurs there, and then consequentially there's an arrival of immune cells to our spatial domain thereafter. And so part of our activities for today is that we're going to generate a separate ODE model specifically for what we'll just call our lymph node. It's going to be a compartmental model with some ordinary differential equations, and we'll just refer to that very simply for the ease of communication. We'll just call that the lymph node. Now, the ODE, after we're done, the ODE model will look like this. So all of the expressions, all of the terms that are highlighted in blue, these are all aspects of the ODE model that we're going to implement in a spatialized and cellularized form through this module. There's lots here, so again, I don't want to spend too much time on this, but we're going to take the cytokine decay in our field and map that onto signaling in what we'll call a lymph node cytokine. So this will be an analogous amount of cytokine in our lymph node compartmental model. That'll then induce immune cells in our lymph node compartmental model. And we will take some of the terms from that ordinary differential equation, which we will simulate in our compartmental model. And we'll take that and we'll map that back onto a rate of immune cells being added into our spatial domain. So if that's clear enough, then let's proceed. I'm going to switch over to Twedit. We're going to begin in the XML. The very first thing that we need is an immune cell. Now, if you don't already have an immune cell in your version of Module 2.2, version 2, then the way you can add this is by going down to the plugin called cell type. If you're following along with the provided code, the plugin should start at around line 19 in the XML. And you should find, if you don't have an entry here already for the cell type, then after the dead cells, I'll just go through the exercise. After the entry for the dead cell type, you'll add another one, and that will look like what's shown here on the left. It'll be an entry for cell type. You'll notice that we are not freezing these cells, so we will not include freeze equals, but instead we'll just go right to type ID. We will give that an ID of 5. It needs to be in quotation marks. And we'll give it a type name in quotation marks. We'll call them CD8 local. This is a specific type of immune cell. Just call them CD8 local. So if everyone's there, we now have another cell type, our CD8 local. These will be the immune cells in our spatial domain. Now, while we're here in the XML, again, this is where plugins are defined and can be instantiated for simulation. We're going to add another one that's built in specifically to control adhesion modeling. Now, what this plugin does is that it assigns coefficients to various type interfaces. So adhesion is modeled by the interface by type, so not two particular cells, but two particular cell types. And the convention is that when we assign lower adhesion coefficients, the corresponding adhesion between the two cell types is stronger. What this looks like in a very simple case for two generic types in the medium, shown here in the table on the bottom. And what you'll notice here is that when following this table, this describes the adhesion coefficients for different type interfaces. And you'll notice here that for a type 1 interface, shown in the middle, this coefficient is set to 5. Whereas moving down to the bottom left, for a contact interface between a type 2 cell and the medium, this coefficient is set to 25. So by this convention with these parameters then, the most adhesive contact interfaces are type 1 contacts. And the least adhesive are type 2 medium. Now, if that's clear, let's add it. So in the XML, anywhere you please, just anywhere on a line that's clear. So move your cursor to a line, maybe add some space if you need to. I'm going to do this under my volume plugin. Now, when your cursor is placed on a line with some empty space, then you can add the contact plugin in the menu bar in Twedit by going to CC3D ML, and then plugins, contact. So the menu bar, CC3D ML, plugins, and then contact. Now, when you click that, you should get a big, long list of XML elements. See, the contact plugin was automatically added by the code snippet generator. And then all of these different entries describe all of the adhesion coefficients for the different types that are prescribed. So if you refer to my screen, the line that I've highlighted, this is describing the contact interface between an infected type and a virus releasing type. And the value in between is the corresponding coefficient that's prescribed for the simulation. Now, one of the nice things about this is that this is automatically generated combinatorially from the types that are specified in cell type. Generating all of these manually is kind of a pain and is quite tedious. So if you change or add a cell type, these need to be updated. Nicely enough, though, Twedit will just automatically regenerate this for you if you just go back and again do CC3D ML plugins contact. Something like that. And while we're here, lastly, the final entry for the contact plugin, it'll have the tag neighbor order. Let's set that to something like 3. This is the range of neighborhood calculations that are made when using contact plugins. So the higher number this is, up to 4, the greater the neighborhood that's used in calculations of the contact plugin. Now we'll leave all of these parameters as 10, so this would be the case of no preferential attachment. Later we'll do lots of interesting things. Well, I'll send you off to do some interesting things by varying some of these and seeing how that affects the corresponding emergent dynamics due to instabilities with differential adhesion. So for now, we'll leave that as is. If everyone's here, then we'll proceed. Giuliano points out in the chat that if also regenerating this code snippet using CC3D ML, that will also automatically reset all of your coefficients to 10. So if you happen to have them set to something, you may want to write them down before regenerating that, otherwise they will be lost. Thank you, Giuliano. Okay, let's continue. Next is cell volume control. So most importantly here is that we model cells that occupy discrete locations. And through the dynamics of the cellular POTS model, that is the cellular dynamics behind CompuCell, the cellular POTS model relies on deformation of cells for them to be able to move, to translocate, so on and so forth. Now, most importantly, when we say that cells occupy some amount of space through those deformations, we also need to impose that those cells will occupy approximately a certain amount of space. And we do that by imposing a volume constraint. The volume constraint looks like the expression shown here. So this is actually the equation that's actually used in the cellular POTS model. And we won't go through the specifics of this, but suffice it to say that the cellular POTS model works to minimize this expression. Now, when you look at the terms here, in parentheses here in this squared term, you have the current cell volume and the difference between the current cell volume and a target cell volume, that being a volume constraint. And you'll notice that when the current cell volume deviates from the target volume, whether below or above, then this term will increase. And this is effectively what imposes a volume constraint onto cells using the cellular POTS model in CC3D. The strength of that constraint is governed by this coefficient that we tend to just call lambda volume, or lambda V. So the higher this value is, the less deformable a cell type will be. Now we can prescribe these in Python, setting specific attributes on each cell object for the target cell volume, or the volume constraint. This can be accessed and written to using cell.targetVolume. And then the lambda volume constraint strength can be accessed with cell.lambdaVolume. Now when we create cells, we need to set these if we're going to manage them in Python, and that's exactly what we're going to do. And as simple as it is to kill a cell and to remove it, to just set the target volume equal to 0. In a couple of simulation steps then, the result will be that the cell disappears from the lattice. CompuCell takes care of that for us. We don't have to do anything after that, and that cell is then effectively annihilated. Now we can add this in the XML as well. This was already added in the code that was provided for module 2.2. But if it's not in your code currently, you can add it as such. You can either type this in manually. The entry is shown here on the left. I also have it highlighted on the right. The plugin's name is simply volume. If you don't have this, there's also a code generator in Twedit. You go in the menu bar to CC3D ML, plugins, volume. Now you notice there are lots of things that are automatically generated here. This is automatically populated based on the cell types that you specified in the cell type plugin. But this is only for the case when the volume constraints and strengths aren't managed in Python, but rather are automatically managed by CompuCell. We're going to manage them manually in Python, in which case all we need is just the very first line with a slash at the end. Just plugin name equals volume, slash bracket, volume in quotation marks. If everyone's there, you can move on. Okay, let's move over to the steppable script. So Glacier model steppables.py. If you're not at the very top of the script, let's move all the way up to the top. In Windows, you can do that with Control Home. Okay, now in the provided code, around line 13, we already have the model inputs for a cell diameter and a cell volume. These are parameters that defined with Josh previously. We're going to add to this with our missing parameter for our volume constraint. Now, you've already done the calculation here at line 14 in the provided code for cell volume. Cell volume is what we'll use as our volume constraint. So we're just going to say in the simplest case that our immune cells will approximately be the same size as the epithelial cells. This is not necessary by any means, but it's a simple case. Now, after that, let's go to the end of line 14 and add a new line. We're going to add a new model input for the strength of our volume constraint. We're just going to call that parameter volume_LM. And we're going to set that equal to 9. Volume LM equals 9. Again, higher values of this parameter will make cells stiffer. Lower values make cells much more easily deformed. Now let's continue. We're going to continue by starting the model string for our lymph node compartment. So again, this is an ODE model modeling the lymph node compartment. We're going to need an ODE model string, and we're going to derive the relevant equations for the lymph node compartment from the equations that we already have in our original ODE model. So we already have ODE model string, and that's describing the ordinary differential equation this is all built from and that we've been modeling and displaying for comparison. We're going to take relevant aspects of this, and we're going to build another ordinary differential equation model string. And let's start that below our current model string. So we have ODE model string in the provided code, starts at around line 32, ends at around line 83. Let's create some space after that model string. And let's declare another model string. Let's call it lymph_node_model_string. This is going to be the multi-line Python string that contains our antimony model of our lymph node compartment. So lymph node model string equals, let's do triple quotes to start a multi-line string. And to start our antimony model, let's enter model, lowercase, space, and then we'll call this one lymph node model, parentheses. And let's return. You can set some tabs here if you'd like. I'm kind of an organizational freak when it comes to formatting of code. Don't mind it on this one. And let's just terminate our model and terminate our model string. So triple quote, model, lymph node model, parentheses, and then the next line just add end, and then triple quote. In Twedit, that should just show up as 2 lines of orange. And this is the string we're going to use to build our model. So let's continue from there. Next thing we're going to do before we start building this, let's go ahead and get the process out of the way of initializing our free-floating model in CompuCell. So let's go down to the start method of our steppable. The provided code, it should now start at around line 109. We're going to scroll down to an entry, there's a comment that says apply initial conditions. This is when the initial conditions of the full ODE model are set based on the simulation conditions in the spatial model below that section. So at around line 150, this is where we're going to add the code snippet that you see on the left of my screen. I'm going to initialize our lymph node model. So let's add a comment here to say what we're doing. Let's say step and then initialize ODEs. And then another one that says generate solver instance, just to let people know what you're doing if someone else wants to work with your code. Now, to add a free-floating antimony model, and this is provided in, the code snippet is provided in Twedit, in the menu bar, CC3D Python, SBML solver, add free-floating antimony model, CC3D Python, SBML solver, add free-floating antimony model. Can get rid of the informative comments since we've already reviewed this feature. Now the first keyword argument is model file, and that's to import a model from a file. We're not going to use that, so we can just delete that. So model file equals model file comment, that can be deleted. We're going to use model string since we're defining our model in a string. We're going to say model, excuse me, model string equals lymph node model string, the string that contains our lymph node model. So model string equals lymph node model string. You can clean this up a little bit by returning before the next argument and aligning it with the previous one shown on my screen and also in the code snippet on the left. Next one, we'll declare the model name, and we'll just give it the same name as declared in the string. So model name equals quote lymph node model. Now our next argument, let's clean this up again by returning, but it should automatically align that with model name. Third keyword argument is step size. We're going to set that to the same as the main ODE model. Step size equals SBML underscore step underscore size. This is a model input. And then our fourth keyword argument that's provided by the code generator is initial conditions. In antimony, we can do this in the antimony model string, so we don't need to do it here. So we can just delete that argument. Give everyone just a second to get that. All right, let's continue. So now whatever we put in our lymph node model string will show up as self.sbml.lymph node model, as thoroughly described by Josh. We will use that quite a few times in this as well. Next step, let's start building our lymph node compartment model. So let's go back up to the top and go to the model string that we started for our lymph node. Then we're going to treat this like something like a black box, which is that there will be information that we pass from the spatial model to our lymph node model. And then our lymph node model will do some calculations based on the equations that we prescribe. And then that lymph node model is going to pass information back to us for the spatial model. In particular, the spatial model is going to pass the total amount of local cytokine. So we're going to do a volume integral of our cytokine field. And we're going to pass the volume integral of the cytokine field to the lymph node model. And then after it's done doing its calculations, we'll then ask the lymph node model, what is the amount of lymph node immune cells? The lymph node model will give us that information, and then we'll use that to calculate the probability of adding immune cells into the domain. So with that paradigm, let's start first by just declaring some inputs and outputs. So let's make a little space on our model string, and let's first add a comment, inputs, so that other people know what you're doing when they go to work with your model as well. They'll know that this is an input. And we use the same symbols as used in the main model string, in which case the local amount of cytokine is C, and we'll just initialize that as 0. We initialize the local cytokine field in the spatial domain as all 0, so we'll initialize the value in the lymph node model as 0 as well. And then we'll start another section, add a comment for outputs. A comment with /outputs, and our output from our lymph node model is going to be the lymph node total number of immune cells. In the ODE model, the symbol was EL, and we'll say that initially EL is equal to 0. And this is the definition of the interface between the spatial model and the lymph node model. Spatial model passes C to the lymph node model. Lymph node model will pass back the amount of lymph node immune cells. Now let's continue. Let's start extracting equations from the ODE model, the main ODE model, that is. And we'll start by first writing the equation for the lymph node cytokine production in the lymph node. In the main ODE model, you scroll up above where we've been working. This is equation E8. In the provided model, it should be around line 41. Let's copy E8 and just highlight all of it and copy. And let's go back down to our lymph node model string. Above our inputs, let's make a little space. Define a new section here with a comment, equations, and let's paste in our lymph node cytokine production rate equation. Now from here, the one modification to make, and this is due to that we're modeling the local cytokine in our spatial domain, is that from E8 that we've copied from the ODE model, we will remove in the rate equation definition in our lymph node model, not the main ODE model, but in the lymph node model, we'll just remove this entry C. And that is because in the ODE model, the dynamics of C, the local cytokine, is explicitly represented by ODEs, whereas in the spatial domain, we handle the dynamics of the local cytokine via the PDE solver. Now we're going to pass that information to the ODE model, in which case all we need for E8 is arrow CL. So this is a source term for the lymph node cytokine. Of particular interest is that the rate equation is proportional to the amount of C, and we will be passing that value from the spatial domain. So this is the coupling of the spatial domain, the volume integral of the local cytokine, mapping that to the production of the lymph node cytokine. Now to use this, we need this parameter KC. Let's just go back up to the original ODE model. In the provided code, KC is defined at line 57. Let's do the same as before. Let's just highlight that and copy it. And go back down to our lymph node model, make a little space after equations, let's define a new section, the comment parameters, and we'll just paste parameters. into that section, the copied line KC. So now we have cytokine production in the lymph node. If we pass local cytokine to the lymph node model, let's go to our next step, which is implementing decay. This is defined according to the ordinary differential equation model. We go back up to the main ODE model string. Let's do the same procedure. Let's copy line 42 in the provided code for equation E9. And just highlight all of that and copy. And back down to our lymph node model. After E8, let's paste that in. And to use this equation, we need the parameter CCL in the ODE model. That's defined in the provided code at line 58. CCL equals 0.5 in units per day. Let's highlight that and copy it. Same procedure. Go down back to our lymph node model and paste that into the parameters section. Moving on, if everyone's here. Let's do our coupling, passing the information from the spatial domain to the lymph node model. Now let's do this in our code, give everyone a chance to provide some feedback on if they're keeping up. In the meantime, for anyone who is with me, we're going to go down to our step function in our steppable. And we're going to start a new section for immune cell recruitment. And we're going to do this at around line 284 in the provided code. In the provided code, there should already be an entry after the viral life cycle, specifically after the transition from uninfected to infected. After that, there's then the step of integrating the ODEs at line 286. Excuse me. Between those two sections, let's make a little space. And then around line 285, let's annotate the new section in our steppable called immune recruitment. The comment I've left is a convention that we've sort of adopted in this code, which is defining each model section with the sort of introductory comment of step. It's in a model step. So at around line 285, let's add the comment step and then immune recruitment. And then below that, let's make a little space. And we're going to pass the volume integral of the cytokine field to the lymph node model. Because again, in our lymph node model, there is a value for the local cytokine, and that value relates to our spatial domain as the volume integral of our local cytokine field. So to do this, let's first add another comment to say what we're doing, which is pass spatial information to ODEs. And to do this, we're going to access the variable C in the lymph node model. We do that by typing self.sbml dot, and then the name of our lymph node model, which is lymph node model. And again, to access the variable C, you can start some brackets. And then in parentheses, enter C. So this is a reference to the variable C, the local cytokine amount in the lymph node model. Now to that, we're going to pass the volume integral of the cytokine field. And we're going to normalize it by the thickness of our sheet because we're modeling something planar. And we're going to do a little scaling according to the derivations of the spatialization that we're just sort of hand waving past for these exercises. Now to do this, we're going to need the cytokine secretor that was defined in the previous module with Josh in the provided code. That's at line around 301. The secretor was called cytokine secretor. So this is a field secretor for the cytokine field. We need that to be able to do the volume integral, in which case you can go down to around line 301. And you can just cut that and paste it above our accessing of the variable C in the lymph node model. Now, let's do our volume integral calculation and pass that to the lymph node model. So self.svml.lymphNode model, the variable C equals cytokine secretor dot total field integral, parentheses. And then again, this is for a two-dimensional model, so we're going to normalize that by the thickness of our domain, which is along the z dimension. You can easily access that with self.dim.z. It's the size of the domain along the z direction. And then our scaling, I'm going to divide this by the scaling coefficient defined with Josh, which is self.scale by volume. Again, don't forget to move the cytokine secretor. It's not shown in the code snippet on the left. You can reference it on my screen on the right. Cytokine secretor was defined below this section of our code in secretion. You can just cut that and paste it right up here above where we're working now. All right. So now we've passed information about immune signaling from our local site of infection to our lymph node model. Now let's do something with that information. Let's go back up to our ODE model for the lymph node. Around now, if you're working from the provided code, it should be around line 85 again, down to line 99. We're going to introduce the production of immune cells in our lymph node by grabbing another equation from the main ODE model, which again should be above where we're working. And the equation is E10. In the provided code, it should be around line 43. You should see E10, and this is a source term for EL, which is the variable for the immune cells in our lymph node compartment. So let's copy that, line 43 approximately in the provided code, and go back down to our lymph node model. Under E9, let's paste it. Now, no modifications required to this, but this does have 3 different coefficients that are defined in the main ODE model: PEL, REL, and KEL. You can grab those from the ODE model as well. So let's go back up in the provided code. It starts at around line 60. PEL, REL, and KEL. highlight all three of those and copy those. And let's jump back down to the parameters section of our lymph node model. After CCL, let's return and then paste those values into our parameter section. Now, if everyone's there, let's add decay. So there's a decay term for the lymph node immune cells in the ODE model. You can also grab that from the main ODE model string. This is the equation E11. The provided code, it's at around line 44. E11, let's highlight that and copy it. And jump back down to our lymph node model, return after E10, and paste that there. Now, with the same logic as with E8, E11, you'll notice here, this is a reaction term for the conversion of EL, the lymph node immune cells, to E, the local immune cells. We'll be modeling the local immune cells explicitly in the spatial domain, in which case we don't need this second half of the reaction term. Instead, we're just going to use this expression just as a sink for the lymph node models, in which case we can just remove E from the rate expression. So the equation for E11 should just say EL and then an arrow, and then a rate KE times EL. Now, to use this equation, we need one more model parameter from the main ODE model, and that's the parameter KE. Let's go back up to the ODE model around line 62 in the provided code. KE equals 0.1. Let's highlight that and copy it. And jump back down to the parameter section of our lymph node model. After KEL, let's return and paste it. Now, this completes the rate equation for the lymph node immune cells according to the ODE model, in which case the next step then is to take that information and then use that to add or subtract immune cells from our local domain. So now we're going to go back down to the spatial model around where we were working when we did our volume integral. And our step function, this is around line 298. Now we're going to do some calculations after integration of the ODE. So self.timeStep at around line 298 in the provided code. This does integration in time of all ODE models that have been defined. Now, after that, let's return and make a little space. We're going to do calculations based on the integrated ODE model for adding and subtracting immune cells. Now, the basic algorithm here is that we're first going to calculate outflow of immune cells, which is immune cells that are in the domain leaving. Then we're going to do inflow, where according to the lymph node model, we will do seeding of immune cells into our spatial domain. And we'll calculate the number of cells that will be added for this step in our inflow calculations, and then according to that amount, we'll then go through and one by one seed those immune cells into our spatial domain. So let's start this by first just outlining the 3 steps of our algorithm here. So after self.timeStep SBML, make a little space and then just add 3 comments. The first one will be our first calculation. Comment calculate outflow, excuse me. After that, we're going to calculate inflow. So we'll add a corresponding comment. And lastly, after that, we're going to seed as many immune cells calculated for inflow. Of course, these comments don't have to be the exact same as mine, just something that's informative enough to be able to follow what you're doing. So with that in mind, let's start by doing outflow. You can see the rate equation from the ordinary differential equations shown at the top of my screen on the left. So this is a decay term for the local number of immune cells. We're going to take this decay term and then we're going to apply our Poisson distribution to determine the probability of removing each individual immune cell. So for each immune cell that's currently in our domain, I'm going to use this rate coefficient defined in the ODEs, and we're going to calculate the probability that each of those immune cells leaves the domain. Now, we're going to use the parameter that's exactly defined in the main ODE model. Now, the rate of removal, according to the ODEs, while scaling to our simulation space, is done as follows. Let's define a new variable at around line 301 under our comment calculate outflow, remove rate. We're going to get the coefficient DE from the ODE model. Self.sbml dot, and then the ODE model was called ODE model. So self.sbml dot ODE model, and then to get DE, we'll start some brackets, some quotation marks, and the symbol was lowercase d, capital E. So that is DE as defined by the ODE model, and then to scale this to simulation time, we'll just multiply this by one of our scaling coefficients, self.scale by time. Now, according to the Poisson distribution, the probability for each immune cell leaving is the same. And we'll calculate that in a variable, we'll call it PR underscore remove. So let's declare that variable, PR underscore remove. This is the probability of removal equals, and then just our Poisson distribution, 1 minus math.exp. Now this is negative DE times, or I'm sorry, negative remove rate. For those of you who've been interested in the scaling parameters, you can get a sense of what self.scale by time is actually accomplishing here by looking at these two equations. Notice that this inc_t, this would be our scaling coefficient for scale by time. This is converting from the rate according to the ODE parameters and its units to simulation time, which is unitless. So 1 minus math.exp parentheses and then negative remove rate. After that, we're going to check the probability over each immune cell in our domain. You can do that with a code snippet, or you can type it manually if you prefer. We're going to visit every cell by type that's CD8 local. So for code snippets, CC3D Python, and visit all cells of given type. Generates a code snippet with some instructional comments. We can delete all of those comments and everything inside of the loop. You should have a loop that says for cell in self.celllist by type. with some arguments. Let's remove the arguments that were automatically generated in the code snippet and then instead say for cell in self.cell list by type, and then our CD8 local cells. So self dot, and then all caps CD8 local. And this is a convention in CC3D. All cell type names in Python are then converted to all uppercase. So for cell in self.cell list by type with the argument of self.cd8 local. Inside of our loop, let's test for removal by rolling the dice, as Josh likes to say. So we'll start an if block, and we'll say if a random number in 0 and 1, random dot random parentheses. It's a uniformly distributed random variable in 0 and 1. If random dot random parentheses is less than PR remove, it's less than our probability of removal. And this block will be executed in return. And in our block, make sure you have an indentation in the next line. If our cell is removed, cell.target volume equals 0. Now, if you recall, the previous slide from this module said we could kill cells by setting their target volume to 0. To say killing a cell is a misnomer here because really what we're looking to do in effect is just to simply remove the cell from the domain, meaning that it left in this case. This is an immune cell leaving the local domain. We're not concerned where it goes. The ODE models just say that it leaves. We can make it leave by setting cell.target volume equals to 0. And that is outflow. Now, if everyone's here, we're going to blast through inflow. As I said at the beginning of this module in my warning, we have a lot to get through. We're going to power right through this. I see no objections in the chat, so we're going to continue. We're going to do calculation of inflow. So we're going to calculate the number of immune cells that are added into our simulation domain according to the information that we get from the lymph node compartment model. And the ODE model describes local recruitment as such, as shown in my screen on the left. You have this first term, KE times EL. So the amount of immune cells in the lymph node multiplied by the parameter KE. Now the corresponding rule in the cellular version is shown here in the next equation. And this, for those of you who like stochastics, this is a cumulative distribution for Poisson distribution. And I admittedly, I will acknowledge that this is not a pretty equation. Well, I think it's pretty, but it's not fun to really go through and dissect. But we can actually very quickly go through and implement this as follows. We're going to do an algorithm where we first ask, are 0 immune cells added? Now this equation tells us the probability of adding a number K immune cells. And we're going to ask first, are 0 immune cells added? And we will calculate the probability according to K equals 0. And if our test fails, then instead we will ask, is 1 cell added? And we'll continue to do this until our test passes, which is we ask, are K cells added? And if the test passes, then we add K cells. And this can be done as follows. So the outcome of this calculation is going to be a variable that we'll call num_add, meaning the number of immune cells added in this simulation step. And we're going to first say that num add equals 0. So at around line 308, num add equals 0. The next term that we're going to define is the rate of addition, which we'll call as a variable add underscore rate. And add rate is according to information from the lymph node model. In particular, the parameter KE, the total number of lymph node immune cells, so KE times EL, and then two scaling coefficients, scale by time and scale by volume. So we can calculate it as such. Add rate equals, from our lymph node model, self.sbml.lymph node model. We want EL, so brackets, quotations, EL. Now let's multiply by KE from the lymph node model. So multiplied by self.sbml.lymph node model, brackets, quotations, KE. And then our two scaling coefficients multiplied by self.scale by time, multiplied by self.scale by volume. Then I have two more terms that we can define to do this with some brevity of code. The third term is calculating the exponent in the probability. This is a constant and doesn't change with K when asking how many immune cells to add. So let's just calculate this now. Let's define this as a variable exp underscore term. Say that exp underscore term equals math.exp negative and our add rate. So the term that's going into the exponent is our variable add rate, and our constant exp term is e to the negative add rate. Now lastly, and this is probably the most algorithmically complex part of this, is that every time that we ask in our trials, do we add 0 cells, do we add 1 cell, 2 cells, 3 cells, every time that that calculation is made, this actually does a summation in the cumulative distribution function up to the number of cells about which we've asked. If we ask, are we adding 3 cells, then in this calculation, this will do a summation up to k or n equals 3 in the expression shown on my screen. Which means that as we ask, add 0 cells, add 1 cell, add 2 cells, we can just simply update a summation term that calculates this value. And we can do this as such. This is shown in the code snippet on the left. Define a variable sum underscore term. And we'll say that that first equals 1. Now sum term is going to be the current value of this summation based on what our current value of k is, our immune cells that we're asking about. And we're going to do this in a while loop. So after sum term, let's define a while loop. Say while, and then let's roll the dice. Random dot random parentheses. And while that value, our uniformly distributed random variable, while that value is less than the current value of the right-hand side of our probability. So while random.random is less than 1 minus our constant exp term times the current value of our summation term, sum term. While random.random parentheses is less than 1 minus exp term times sum term. And let's add a colon and go into our while loop by returning. Now every time we make this test, we will increment our output of this step, which was num add, again the variable that describes how many cells are going to be added, num add, and let's just add 1. Every time we ask this question, every time that this test fails and we do this while loop again, we will increment our output by 1. And for the next test, we're going to update our summation term. And we can do that as follows. Take our sum term and we're going to update it. So sum underscore term, we're going to add to it by saying plus equals. So adding to the current value of sum term. The equation is our add rate, add underscore rate, to a power of num add. You may have noticed by now, when getting halfway through this, that our num add is acting something like the value n in the cumulative distribution function. If you follow in that way, then the rest of the expression follows. So sum term plus equals add rate to the num add. And then we're going to divide that by the factorial of num add according to the cumulative distribution function. So divided by math.factorial num underscore add. Question in the chat, can we use here random.poisson? That is a great question and one that I can't answer off the top of my head. If you email me, well, if you're telling me that you can, then that's great, and maybe this could be improved to add a little brevity to the code. If you're asking because you don't know, then email me to remind me and I'll look it up after this module. Yeah, great question, Romain. Okay, so, and that completes our algorithm, actually. So when this test fails, then the current value of num add is the number of cells that are being added. Now from there, you can finish this by moving on to immune cell seeding, the last section that we outlined for the spatial aspects. Romain in the chat says, real NumPy, so I guess it should work. Yeah, this is a great question, Romain. We should talk after this. I hadn't even thought at the time to look into it. Okay, so our seeding algorithm. Go down to, should be around line 316 if you're working in the provided code. I'm going to do a return after our comment to seed as many immune cells as calculated for inflow. I'm going to correct my comment. Immune cells as calculated for inflow. Okay, now to do this, we have a certain number of immune cells that we are going to add for the simulation step. It could be 0, in which case we won't do anything. It could be multiple. Now, the way we're going to do this is that for every cell that we're going to add, according to our previous calculations, we're then going to go through, we're going to randomly select a pixel that's not occupied by a cell. And then we're going to put an immune cell in it. So we're going to randomly select an available site in the spatial domain. We're going to create an immune cell, and then we're going to put that immune cell in that randomly selected available space. So to do this, I'm going to start by just doing a for loop after our comment for seeding. We don't actually need what's returned by range in this, so we're just going to say for, and then we'll just add an underscore. For underscore in, and then range. Let's make sure that num add is an integer, so range of int of num add. For underscore in range of int of num add. So whatever goes in this for loop is going to be executed as many times as is specified by num add according to our inflow calculations. So let's terminate that with a colon and start our for loop by returning. Should get an indentation automatically. And then let's annotate our 2 steps. First step is we're going to get a random medium pixel. Comment, get random medium pixel. Let's return twice and add a second comment, add a immune cell. And these are our steps. So for every value returned, we're going to get a random medium pixel and add an immune cell. Let's continue. Now to get a random medium pixel efficiently, we can turn to another plugin provided in CC3D. Let's go to the XML and we're going to add a plugin called Pixel Tracker. So in the CC3D XML, wherever you please, anywhere on an empty line, place your cursor. And in the menu bar for CC3D ML, you can go to Plugins and Pixel Tracker. Now what Pixel Tracker does is it keeps track of all of the pixels, or voxels rather, in a 3-dimensional simulation. It keeps track of all of the sites occupied by each cell in the simulation. It's a very efficient way to retrieve all of the locations where a cell can be found. And if so told, Pixel Tracker will track the medium, meaning that you can also very efficiently get an iterator over all of the voxels in the simulation domain currently occupied by the medium, which is to say not by any cells. And we can enable this in our Pixel Tracker if we added the plugin either manually or using the code generator in Twedit. You can enable medium tracking by just adding the tag track medium /. This is not automatically enabled because it can be a bit computationally expensive. Not too bad, but we make it an optional feature. Now back in the steppables, since we're going to use medium tracking in our annotation for our section get random pixel, let's then add an additional comment that says needs medium tracking, because we're going to write code that relies on medium tracking being enabled. Now with that, if everyone's with me, let's get our random medium pixel. So Pixel Tracker plugin has a nice command called get medium pixel set. This just returns an iterator, the iterator that I was just describing, over all of the current medium pixels. And the full command to do that is self.pixeltracker.getMediumPixelSet. It's shown on the left-hand side of my screen. Now the iterator that's returned by getMediumPixelSet is called Pixel Tracker Data. You tend to just write it PTD. So each pixel tracker data will have an attribute pixel, and each pixel will have the coordinates of the particular pixel. Coordinates being X, Y, and Z. So in short, to make a Python list with all of the pixels occupied by the medium can be done as follows. Let's declare a variable called med for medium, pixel set, med underscore pixel underscore set equals, and let's start a bracket. Now self.pixeltracker.plugin.get medium pixel set returns pixel tracker data. We're going to make a list with one line of code. We're going to do this as follows. Inside our bracket, let's do ptd.pixel. ptd being the pixel tracker data iterator that's going to be returned in the for loop that we're going to specify in this bracket. So ptd.pixel, and then just write what you would for a for loop. For ptd in self.pixeltracker plugin .get medium pixel set parentheses. So this is a Python list of all of the pixels currently occupied by the medium according to Pixel Tracker plugin. Now, in that list, we would like to draw a random pixel, and we can do that by generating a random index in the Python list. And we can do this as follows. Let's declare a variable rand underscore idx for random index, and that equals, I'm going to use a function defined in the random module, random.randint. Let's start some parentheses. We have two arguments. The lower bound of the range that will draw a random integer, and the upper bound is the length of our list of medium pixels, and we're going to subtract by 1 because of some of the specificity of this particular function. So the first argument is 0, that's the lower bound, and the upper bound is the length, len, of the medium pixel set list, med pixel set, and then subtract by 1. So this will draw a random index in the size of our list of medium pixels. Now let's get our random pixel. We do that by declaring a variable rand underscore pixel for random pixel. And easy enough, rand pixel equals med pixel set. So our Python list, start some brackets, and you probably guessed it, at our randomly selected index. Now we have our randomly selected pixel or voxel. Now let's put an immune cell there. So below our random pixel, let's declare the two coordinates in our plane where we're going to place our immune cell, and we can do that by just unpacking the pixel that we've selected. We can do that with two variables that will declare x underscore seed for the x coordinate of the seeding site equals rand underscore pixel, our random pixel, dot x. And the same for the y coordinate, y underscore seed equals rand underscore pixel dot y. We don't need to get the z coordinate because in the model that we've been building, our immune cells go into the coordinate z equals to 1. So our immune cell will be placed at x seed, y seed, 1. Now moving on, we have our seeding location. Let's go down to our second section, add immune cell. And let's make some notes about what we're doing. All we're going to do is we're going to create a new immune cell, just like how we created epithelial cells with Josh. Then we're going to place it in the cell field at our seeding location. And lastly, we're then going to set necessary volume parameters, our volume constraint and our strength, our constraint and our strength, using cell volume and volume LM, our model inputs. So to add an immune cell, first add the comment, create new immune cell, and the function is self.newCell. This will return a new cell according to the type that we pass to self.newCell. So cell equals self.new_cell. There's a Python code snippet for this as well, though I'm blanking on what it is at the moment. So suffice it to say that it's there, and this is what it would return. Self.new_cell, and let's pass the cell type that we'd like to create, which is our CD8 local cell. Cell equals self.new_cell, passing the argument self.cd8 local, again all caps, by convention in CC3D, for necessity rather. Next section, now let's add the comment. We're going to place our new immune cell. And as a reminder, we can just get the cell field with self.cellField. We can index into that like a NumPy array, and then we can just place cell that we just created wherever we've indexed. In which case, for here, we're going to index into our randomly selected pixel, and that's self.cell_field, our cell field, starts in brackets. And then our x-coordinate, which was x_seed, our y-coordinate, y_seed, and our immune cell layer, z equals 1. So self.cellField at x seed, y seed 1 equals our new cell, which was just cell. Giuliano mercifully reminds me in the chat that the Python code snippet to create a new cell is in CC3D Python cell manipulation create cell or cell detail. Thank you again, Giuliano. Much appreciated. Now, in our last step, since we're managing the volume plugin in Python, we're going to set our volume parameters. And those were cell_volume and volume LM. Let's note what we're doing. Set volume parameters. And let's first set the volume constraint, which was cell.targetVolume. And we're going to set that to our model input of cell_volume. And likewise for the volume constraint coefficient, our model input parameter value is at volume_LM, cell.lambda volume equals volume_LM. So we set our constraint and the strength of our constraint according to our model inputs for the cell that we created at our randomly selected site. And we're doing this for as many cells as is instructed by our calculations for inflow. And that is the entire spatialization of immune recruitment. Now, I'm going to turn it to all of you to go through the exercise of updating the population data windows. So we had, for example, we start the module in player that we're working from. We have one of our Windows population data. And we have tracking for CD8 local and CD8 lymph node cells. And I would like to give you about, say, 10 minutes or so, maybe go a little bit shorter depending on how everyone's doing. Go through and in the data plotting defined in Twedit for the population data window, want to update the plot according to the number of local immune cells and the number of immune cells in the lymph node. Let's say, let's take 5 minutes. I'll let you have a go at that, and then I'll complete it along with you after that. And if you get far enough and you get it implemented, you can test everything out and see how it went by going over to player, running the simulation, maybe doing a little debugging for any typos. I'll probably have to do the same. This is typical for this sort of work. And if it works, and you can actually get the simulation to run, go ahead and run it and see what happens. Gonna get a poll going here in a minute to see how everyone's doing. Give it another 2.5, 3 minutes or so, unless you hear back that everyone's gotten through this. All right, last call, got about another minute. If anyone's still working, feel free to drop it into the chat and mention it. We're at near the final leg of this development, so no worries if you don't get completely through this portion. The rest of this is all pretty much secondary work and mostly content that I've gone through in much more detail with Josh. All right, so let's go through this and see how everyone is doing. Polls open now. You can pause for another minute if we've got consensus that would like me to wait. Got a few still working on it. That's fine, no problem. Give it another minute or so, and then maybe those of you who are still working on it can follow along with me as I go through it as well. All right, so got some people working, so that's fine. I'm gonna go through this as well, and when I catch up with you, if you're still working, then just follow along with me. Try and push this past the finish line and see this thing work. Or not. It happens sometimes. Now, first, at around line 201 in the provided code, we need to add 2 new data plots. We've got specification of the 4 different epithelial cell types. Now let's do specification of our 2 different quasi-immune types. One being an actual immune type in CompuCell3D, which was CD8 local. So that's a cell type that's defined in the cell type plugin. I'm going to use dots with dot size, and I'm going to make my dots white. And then I'm going to do another one for the immune cells in the lymph node. I'm going to call that CD8 lymph. And I'm going to set the color for my lymph node immune cells as purple. So now I'll have 2 more plots that will show up, or 2 more sets of data that will show up in my population data plot window. Now I'm going to go down to where we were working in the step function and then update those 2 plots in the population data window with the current values according to immune cell recruitment. So we wrapped up our calculations for immune cell recruitment in the provided code at around line 335. Should be before the next section that's labeled as secretion, which you did in the previous module today. Let's make a little space before secretion starts, and let's do our data plotting. So let's add a comment saying what we're doing. Plot immune cell population data. And let's first start by actually calculating the number of cells in our spatial domain and in our lymph node. Let's say for the local cells, say variable num underscore cells underscore immune equals, and then we're going to use self.celllist by type, and we're going to measure the length of that list. So the length of what's returned by cell list by type is the number of the cell type that we pass. In our case, we're going to pass self.cd8 local for our local immune cells. So do len for length and then self.celllist by type, and pass our local immune cell type, which is self.all caps cd8 local. And for our lymph node, let's declare another variable called num underscore cells underscore immune underscore L. the number of immune cells in the lymph node. This will just get directly from the lymph node compartmental model. The variable is EL. We can get that value using self.sbml.lymph node model. So typo in my code snippet in my slides. Refer to my screen on the right. It should be self.sbml.lymph node model. And starts in brackets and some quotations. And again, the symbol was EL, capital E, lowercase l. Now, the trick here, due to some of the details of the multi-scale scheme, is that the lymph node models an organismal level response, whereas we are modeling a local tissue patch, in which case our immune cells in the lymph node have to be scaled to our patch. And we can do that by multiplying by our scaling factor for volume, which is self.scale by volume. And then add them to the data plots for our new entries in the population data window. So in this case, the window is self.pop_data_when, and then using the function add data point for our CDA local cells. I'm going to convert the time to days. So MCS times days to MCS, and then just the number of immune cells in our local domain, as we calculated around line 338. Same for our lymph node. Whatever entry you specified for adding your data window for the lymph nodes, I called my locals CD8 local and my lymph node immune cells CD8 lymph. And then again for the x-axis, it's the simulation step converted to days, so MCS times days to MCS. And then the y-axis for this plot is our number of immune cells in the lymph nodes scaled down to our tissue patch, which is num cells immune L. And that completes that exercise. Now from here, all we have is exercises, and I'm thinking that to save on time, since we've been falling behind again, is to send everyone off to work on this on their own time. Can run this very quickly in my player and see. You can test your implementation after having completed the previous exercise. You can do a little debugging by going over to player. Make sure you still have the code that we've been working on loaded into player. You can test to see if everything was implemented properly by just hitting run. See if any bugs pop up. In my case, I miraculously managed to write all that code without any bugs. I'm going to maximize my player. Now, if you entered everything correctly, and if you didn't, no worries. That's a lot of code. And again, debugging is half the fun and most of the pain. And so if it doesn't work exactly and you can't get this to run, that's no problem. The cells, or the slides, the cells, that's funny. The slides to do this are made available to everyone, and that's all step by step. The current state of the code, as you see it here now, is actually the module 2.3 that's also been shared in the student materials. And so if you get tired of debugging and don't want to fight with this, then you can find a working version in module 2.3. Now in mine is working. I'm plotting the immune cell layer of my cell field on the left. And in particular, see, we don't have any immune cells yet, which is fine. There's a delay. Now, when I expand my population data window, and I look at the very bottom here, the purple dots, as I define them, the lymph node number of immune cells were purple. And I see now, even though the value is 0 currently, I see that in my population data window, I now have a value showing up for the number of lymph node immune cells. And as my simulation goes on, I see that value rising. My uninfected cells by around 1 day is 0. Everything is at least infected. And now I see that my data points for the lymph node immune cells are now greater than 0. So it's doing something. Again, this is the value of the immune cells in the lymph node according to our compartmental model. So this is not the number of immune cells in the spatial domain, which is still 0. They haven't shown up yet. But as simulation time progresses, we should see the immune cell value rise, first for the lymph node and then later on for the immune cells. And we can see if some of them show up. Got a note in the chat from Peter. Rand N tells me I've passed it, and is that an impossible range? Impossible range? Say, make sure that you are passing from 0 as the first argument to the length of the Python list of medium pixels -1. Also be sure that you completed the step of enabling medium pixel tracking in the XML. I think that would throw an error if you tried to call get medium pixel set and hadn't enabled it. Now, for those of you who are running it, my simulation is past 700 steps, and I finally have immune cells. And I look in my population data window, and there they are. Lymph node immune cells rising, over 200 of them currently. Now I've got some white dots showing up. There's my local immune cells tracking. No effects from the immune cells, so no contact killing or anything like that. For now, they're simply there. Now, if you don't feel like debugging through all of that code, then again, feel free to grab module 2.3. It's in the student materials that have been shared. I'd like to send you off with a final exercise to do on your own after the workshop today. Maybe make a note of this. The exercise is to vary the contact parameters between the immune cells and then run it in simulation. Specifically, we set contact plugin up so that there's no preferential attachment, and instead that everything was evenly adhesive to each other. And the question is, what happens when immune cells stick to each other versus what happens when they don't stick to each other. And so the experiments that I would like to send you off to do on your own time is to first set up contact parameters that implement each of these cases. Now you can do this by, say, setting everything to 20, and then for immune cells that stick to each other, set the adhesion parameter for the CD8 local cell interfaces. If everything else is 20, then set that to 10. Or if everything is 10, then set that coefficient to 5. And then in the opposite case, to make them not stick to each other, if everything else is 10, then set this to, say, 20. Now, run both of those cases long enough to really see some immune cells coming into contact or potentially coming into contact, and observe the distribution of the immune cells spatially, and then based on what you observe, consider the following question, which is that if killing of infected and virus-releasing cells is local and driven by contact, then how would the location and distribution of the immune cells as affected by preferential attachment and differential adhesion, how would that affect the efficiency of immune response? Now with that, I would like to turn it over to James to see what we're off to next. We have another module scheduled after this one. Can try very hard to finish that up before 6. Need to take a break very briefly, James, to get myself some more water, and then can try and press through the next module.